average model?
This is average model, yeah.
VL pole will be the voltage will be 0 for inductor.
Right.
The current capacitor.
So, and then when we come back, we'll do flyback and forward. I've got 4 demonstrations, one flyback and then flyback in parallel, and forward in parallel. So, and then we'll get into stability analysis and try to wrap it up as quickly as we can. I know it's been 2 long days. When we had the crash of the plane in the Pentagon, they had really shut down the whole DC, area. Let's go ahead and do. I think this. We'll skip the slides here and go directly to the 4 demonstrations we have, and. I don't have the average model for flyback, so we just want to do cycle by cycle. So this is a flyback circuit. We have a transformer here, and you can see that the polarity, of course the diode here is connected to the reverse polarity here, and the way we have simulated the transformer, we essentially have this parameter file called transformer non-ideal, okay, and we are using 2 coils, L coil 1 and L coil 2, okay, and they have coupling L coil 1, L coil 2, and they have coupling of basically parameter K. So if you look at parameter file, so L coil 1 here is where is L coil 1? I can't even see it.
L1 is called
L1 30 micro. Yeah, 30. Thank you. 30 micro, and L2 is 1.875 micro, right? So that essentially is the ratio of square root of L1 by L2 decides your turns ratio, okay? Because L1 is proportional to N1 square and L2 is proportional to N2 square. So you have so the turns ratio for the transformer is essentially square root of L2 by L1. And so here, everything pretty much remains the same. And we have some initial currents just to stabilize the simulation. I coil 1 of 1.17 amps and I coil 2 of 0 amps. If we run it, so we have a simulation profile up to 1 millisecond. And let's see, we have an input voltage here of 32 volts. Okay, so let's run it. All right, so we have a running simulation. We're going to go to a new window, and let's first look at the current in the switch, primary switch. Okay, so that's your switch that's your primary side switch current. You can expand it. Essentially, that's what it looks like. Okay. And we can also look at the secondary current. So the diode. So they should be out of phase. Maybe this is a bad idea. The output voltage. That's your output voltage. So if we zoom out, that's how the waveforms look like. So you have the primary side, the diode side, those are your three waveforms. Okay. Now on the, and then let me open up Flyback in parallel. Now here what we have done is we have two PWM channels. So one PWM is shifted by 1/2 of the time period. So actually you can essentially double up your switching, your ripple here, and you can also essentially doubles your switching frequency without actually having to have a fast switching PWM. So here what you have is the outputs are paralleled. So these two diodes are actually feeding the same load, C and R, and consequently, and these switches are 180 degrees out of phase. Now here, because the duty cycle is less than 0.5, so we are able to do that. So you have these are out of phase, so we can go ahead and simulate it. And let me just show you how we have done PWM shifting. So we have got now, this is a delayed PWM, and all we have done here is added this term . So we added pi, additional pi to this term. This was only, this was pi by 2. Now it is 3 pi by 2. This term was pi by 2. So it is now 3 pi by 2. Okay, so we have added pi to this function. So as a result, the PWM is shifted by 1/2 of the switching frequency or of the time period, right? So as a result, you have, you essentially, let's close this a little bit. So we have a gate drive 1, which drives the top one, and then we have gate drive 2, which drives the bottom one. Okay, so let's go ahead and run the simulation.
In practice, the DC source, there are two sources or just one source?
One source. One source. One source. So let's see if we can go ahead and plot. Let's see. Oh, I see what it
You
is.
have made two sources, but in practice it was just one.
Yeah, it is one. We have, this is a 1K resistor here. Actually, you can take this out because this guy here is connected here. It's simply I think, yeah, this is connected now. So we can actually go ahead and rerun this. And if we add what we're going to do is first look at the PWM signals. So let's go ahead and look at PWM gate drive. So let's go ahead and look at the gate drive 1. This is the gate drive. We'll zoom in to, let's say, and then for that further, and then we'll add the gate drive 2. So you can see that they are essentially offset by 180 degrees.
But there is also a gap between the two. Dead zone.
The gap is because, no, it's not a dead zone because the duty cycle is 0.4.
0.4. It's 0.5 to the exact.
Oh.
Right. So the duty cycle is 0.4. So you have got, after 0.5, the second pulse will start. Right. So essentially this doubles up your doubles up your ripple frequency, fast ripple frequency. And if we now go ahead and look at, let's go ahead and look at, I'm going to add plot here, and we will look at the current for switch 1. So this is switch 1 current, and we'll also plot switch 2 current. So they are, as you can see, phase shifted by 180 degrees. And then if we don't have a tertiary winding yet. You can add the tertiary winding, but we don't have the tertiary winding yet. Okay, so, and if you look at the output current, let's look at our D1 and D2 current. So what we're going to do is plot the window, and we look at D1 current, and then go ahead and look at D2 current. So those are your D1 and D2 currents, which are overlapping simply because they have a 60% duty cycle compared to the 40% on the other side. And if you look at the capacitor,
Output voltage.
capacitor, so that's for a new window, and I want to see so this is our output voltage. So it's about, if I take my cursor, it's about 4.9 volts. Okay. And if I were to do FFT,
the time window, I think you need to define. This
That
one
in this FFT, that peak which it is showing, that should be exactly 2 times the switching frequency. No?
so that is what I was hoping to see. But this peak here,
10 kilohertz.
10 kilohertz, and I think our switching is actually 100 kilohertz. So 200 kilohertz. This is 200 kilohertz switching. So actually, I was hoping to see.
At 410 kilohertz.
Yeah.
Yeah, there is a peak.
Yeah.
So you have a peak at 400, right? But why there is a peak at 10 kilohertz?
That's an artifact. You have to actually just take one period so that you get this compared wrong. Right now it's taking the entire data right from the transient.
Right. Right.
If you take, select it manually, you're calling it on that 10 kilohertz.
Okay.
If you take it on the steady state, then
Yeah,
you will get
only
only
the
this.
steady state.
That it must be taken in the
Right.
transient.
From the start. From
The initial
start.
transient.
That's right. That's right. Yeah. That's a good point. Okay. So, and then let's go ahead and do the forward conversion. I'm going to close this. Okay. So close this guy also. And let's go ahead and open the forward. So this is the same transformer used in Flyback, except that we have used the forward configuration. So the polarity of the transformer, so when you have current flowing here, you have a current flowing in the diode. So this is a forward converted configuration. And here, we're using the values. So we have V input of 50 volts, L1 of 100, L2 of 6.25 microhenry, L1, and then we have got C of 100 and R of 1 ohm. Sitting at 200 kilohertz. So let's go ahead and do this. So we have an inductor and a capacitor here. You didn't have an inductor in the Flyback. So if you go to new window and we say we want to look at the primary current, switch current, we're going to attach this probe, and that's your switch current. And then if you want to, let's just position it to 0. And, we'll add another axis to it. And let's go ahead and do the secondary current. So this is our secondary current, and if we zoom in, so your green one is the primary current, and the red one is the secondary current. So they both conduct at the same time. Their actual zeros are not lined up. Probably could line up the zeros just to see the effect. You can kind of see the. Okay. And then if you want to go ahead and see the output voltage, that's your output voltage, right? And we can definitely go and see this current here, inductor current, and that's your inductor current. A nice ripple to it, and it goes to 4 amps. Okay, and then what we'll do is close this project, unless anybody wants to see any of the waveform. Alright, so we'll close this project, and we will do forward in parallel. here the same concept as Flyback, except that, and then you got two PWM channels delayed by 1/2 time period, and so getting fed from the same source, and then they're getting connected to a same output circuit, right? So we'll go ahead and run this. Okay, and if we go ahead and plot the two currents, and that's your one primary current, and then we'll plot this one. That's your secondary current, so kind of should be shifted. Yes, they are shifted by 1/2 the time period. And we position them at 0. And then we can go ahead and do the same thing on the outside. We can plot the diode currents. And then plot this one. See that something kind of happened. Okay, so that was the forward converter in parallel, right? So that finishes that demonstration, and what we'll do is go through the stability analysis. And then we have, try to wrap it up. Okay. So